Who hasn't dreamed at least once of being able to move in time as you move in space, of being able to visit the past and the future? It is no coincidence that time travel is a fundamental ingredient of the most successful science fiction works. Surprisingly, physics seems to at least partly leave open the possibility of time travel. Einstein's relativity considers time a dimension, in some ways similar to the dimensions of space. But then, are time travel feasible? Let's try to understand it. By the way, can we travel in time? As incredible as it may seem, the theory of relativity does not completely exclude the possibility, but we must understand it well. Travels in the future are certainly possible. Einstein has shown us that it is enough to move at high speed relative to another observer, or to get close to a large concentration of mass to experience the effects of time dilation. Time flows differently in different reference systems, and not figuratively or simply because the clocks go at a different pace. In any way you measure the passage of time, including biological aging, the result is the same. If I could travel at speeds close to those of light and take a tour in space, returning to Earth, I would find that a few months or years have passed for me, while decades or centuries have passed on our planet. I would literally have traveled in the future. The same thing would happen if I got close to a neutron star, or a black hole, where gravity is very intense, and then went home. For me, during the permanence close to the massive object, time would have passed more slowly. So again, I would find that those who remained on Earth have aged much more than me. As I said in other videos, this effect of time dilation due to speed or gravity is not only theoretical, it is measured, for example, in elementary particles, which, when they travel at speeds close to those of light, have much longer lifespans than when they are at rest. If they could speak, the particles would say that they have traveled in the future compared to their peers who have remained stationary in the laboratory. There is therefore no doubt that travel in the future is possible, and that their practical realization is only a matter of technology. In fact, since each of us moves continuously compared to the others, and experiences small variations in the gravitational field, we also move in the future in a slightly different way from all the others. However, to experience the effects of time dilation in an evident way, we should move so fast that the thing at the moment is in fact unrealizable. But this is not exactly what we have in mind when we think of time travel. The traveler in the future, in fact, would have no possibility to go back to the time of departure. He could only go forward in time, deciding in advance at what speed and on which path to travel to obtain the required time dilation. But he would only be traveling in time in one direction. To be able to talk about time travel, we should consider the possibility to go in both directions, and therefore to travel even in the past. But here things become more problematic. Naturally, there is an obvious way in which we can see events that happened in the past. Just look far into space. Since light travels at finite speed, when I look at a distant object, its image comes to me with a certain delay, which in the case, for example, of the most distant galaxies, can be millions or even billions of years. So, when we look inside a telescope, we are literally looking back in the past of the universe. And this method is very useful in astronomy because it allows us to reconstruct the history of the universe and the objects it contains. But we cannot use it to look at our past. For example, to see what the Earth was like at the time of the dinosaurs, 100 million years ago, let's say, I should have a very powerful telescope and observe it now from a point 100 million light years away. But to reach that point, starting now, I would certainly take much more than 100 million years because I can't go faster than light. So when I get there, looking back, I won't see the dinosaurs. At most, I could see what happened after my departure. So we cannot deceive the law of cause and effect. To really travel in the past, we should make what in relativity are called closed time curves. We know what a closed time curve is in space. It is a path that takes us back to the point where we started. A closed time curve is a trajectory in space-time that not only takes us back to space, but also takes us back in time. So, the question we have to ask ourselves is, does physics admit the possibility that there are closed time curves? The answer is yes. In the theory of relativity, the existence of closed time curves is allowed. Solutions of this kind were found for the first time in the 30s and 40s of the last century, for example by mathematician Kurt Gödel. But those solutions were, in fact, simple mathematical curiosities at the time. They showed that general relativity does not prohibit closed time curves, but they did not say if and how we could actually make them. But today we know that, at least theoretically, there are physical situations that can produce closed time curves. For example, in 1974, the physicist Frank Tripler proved that around an infinitely long rotating cylinder, there would be a region containing closed time curves. But it has never been proven, for example, that even a cylinder of finite length can obtain the same effect. Closed time curves also appear in the solutions of general relativity that describe the interior of a rotating black hole. And perhaps the most science fiction possibility offered by physics is the one found in the 80s by Kip Thorne and his collaborators. Thorne's idea for time travel includes two ingredients. First of all, you should have a wormhole at hand, that is, a cunicle in space-time. On the channel, you will find another video in which I explain better what it is. The second ingredient would be the possibility to move one of the wormhole openings compared to the other at speeds close to those of light, then bringing it back to the starting point. Due to time dilation, the time spent on the side of the opening that traveled quickly in space is less than that spent on the other opening. It is exactly what happens in the famous twin paradox that I told you about in another video, only that here, instead of two people moving one compared to the other, there are the two wormhole openings. So one wormhole opening goes around and returns to the starting point. What happens after moving one of the two openings is that this opening is no longer synchronized with the other one. So if you enter the opening that has moved in space, going out of the other side, you find yourself in the future. And vice versa. If you enter from the opening that has remained stationary, going out of the other one, you go back to the past. So we would have made a time machine that would allow you to move back and forth in time, even if only with a fixed length temporal leap, which depends on the trajectory accomplished by the opening that has moved in space. And also, you could not go back to previous times when the machine was created. There is no need to emphasize that all this is simply a theoretical exercise, and building such a conjecture is entirely impossible as far as we are concerned. But practical considerations aside, the fact remains that time travel does not seem to be excluded from the theory of relativity. However, there are many reasons to doubt that nature allows them to be realized. As we know from science fiction, traveling in the past produces enormous paradoxes that do not seem easily overcome. For example, what would happen if, traveling in the past, I prevented my parents from recognizing each other? And if I altered the course of historical events, what would I find going back to the time I started from? And also, if closed temporal curves are possible, what sense would it make to talk about cause and effect? I could no longer say that an event precedes another, just as I cannot say that a point comes before another on a circumference. And questions like these make traveling in the past rather problematic from a conceptual point of view, and many have imagined that nature may have found a way to prevent them from being realized. Stephen Hawking, for example, popularized this concept by renaming it chronological protection conjecture. For example, according to Hawking, a future theory of quantum gravity that exceeds Einstein's theory of general relativity could have as a consequence the abolition of closed temporal curves, or the impossibility of building a stable wormhole, and so on. The physicist Igor Novikov, on the other hand, hypothesized the existence of a principle of autoconsistency, that is, a mechanism that prevents an event from changing that has already happened. In other words, what has happened, including the fact that a traveler has gone from the future to the past. Any sequence of events is unalterable, so if I went back and tried to change the past, I could not succeed, because even my attempts to change the past would have already happened. In fact, they should already be included in the story that precedes my departure. But the real obstacles to travel in the past are probably born from thermodynamics. So far, in fact, I have only talked about the time described by the theory of relativity. The arrow of time, or the fact that time seems to pass from the past to the future, is not written in the fundamental laws of physics. The apparent flow of time is rather a macroscopic characteristic related to the behavior of the enormous number of particles of which the real world is made. The direction that goes from the past to the future is the one towards which a physical quantity called entropy grows. If we introduce entropy in reasoning, we see that in reality, it is not possible to travel in the past in the way we would like. That is, keeping in mind everything that has happened to us up to that moment. Why? Because all the mechanisms that keep track of previous events, including our memory, do so by increasing entropy. But evidently, entropy cannot grow along a closed curve, because otherwise we would have a contradiction. That is, the same system should have two different values of entropy at the same point in space-time. It would be like climbing a climbing ladder and finding yourself at the starting point. So, if there was really a closed time curve, entropy should remain constant along the curve, but in this case, we could not have any memory or perception of the passage of time. Okay, but what would happen if we could reverse the meaning of the passage of time, bringing entropy back to the initial value? Well, in this case, we could not say that we have traveled in the past. We would have reversed the film, but from our point of view, we could not notice any difference, because we would continue to call the past the state with the lowest entropy, which would be the only one of which we could have a memory. So, to summarize, relativity tells us that we can certainly travel in the future, but although you leave open the possibility that there are closed time curves traveling in the past, seems to be excluded in the real world. If you found this exploration of time travel intriguing and want to dive deeper into the mysteries of the universe, don't forget to subscribe to the channel. We'll keep unraveling fascinating topics like wormholes, relativity, black holes, and much more. Hit the notification bell so you never miss an episode. The journey through space and time is just beginning, and you won't want to miss what's coming next. Thanks for watching, and see you soon.